Good evening and welcome to the College of DuPage. I'm Joe DalSanto, astronomy professor here, and I would like to welcome you to our discussion on black holes. Pleasure to have you all with tonight. Hope to explain a lot about this mysterious topic that people often wonder about when astronomy comes up. I always say science is not just for scientists, but really it's for all of us to enjoy. And so that's my intention, is to try to share with you what we've learned, see what an amazing universe that we live in. So black holes, quite the topic. Probably a lot of questions come to mind. We'll start out with some simple, obvious ones. What is a black hole? Where do they come from? Those kind of questions anyone would ask. What are they like? Have we found any yet? Well, to answer that question, I'm going to start our discussion by talking a little bit about stars, because the short answer is that black holes come from stars. And so we'll take a few minutes and we'll talk about how stars live and especially how they die, and then we'll be able to see where black holes come from. We'll be able to understand them that much better. So let me give you a brief overview. You can see a few notes here. Up on the top right, we see a diagram illustrating a lower mass star. And on the lower right, we see a diagram illustrating a higher mass star. And I'm just going to walk you through this briefly. Stars are made of huge amounts of gas. Out in space, we see huge clouds that slowly, gradually form new stars under the force of gravity. Now, of course, this takes a long time for gravity to work. It's a fairly weak force in this context. But over time, this cloud will slowly have different areas of it where stars will contract. Gravity will bring this material together, compress it to higher densities, higher temperatures. And eventually, in the very center of the star, the temperature will be so high that nuclear fusion will begin. The star will begin changing hydrogen into helium. This will produce vast amounts of energy. So this new force outward is going to balance the relentless pull of gravity inward. And thus we achieve a stable star. Now I've greatly simplified, of course, but that's the general picture of star formation. Turns out that lower mass stars will live a very long time, often billions of years. Higher mass stars will not live quite so long, maybe some millions or tens of millions of years. But sooner or later, both types of stars will change. Why? Because they will use up the fuel that is providing their energy. And so eventually, relentlessly, gravity will again go back to work to change this star. So we're going to see here that low mass stars are going to go through some changes. First of all, they're going to expand, as you can see in our diagram, and become a large red giant star. They're going to go through some other changes, and they're going to expel their outer layers out into space. And all that's going to be remaining is the very small, dense core of the star. It's very hot. We call that a white dwarf star. And that's basically the end state of a low mass star. High mass stars, though, on the other hand, they have a more dramatic fate. They're going to also go through some changes, which I won't go into great detail. But at some point, they're going to change into supergiant stars, some of the largest that we know of. And after, again, various changes occur, they're going to explode violently. And all that's going to be left is a very tiny, even denser, even hotter core to those called a neutron star that we'll be talking about. So this is a very short summary, of course, of how stars change, sometimes called stellar evolution. But it sets the stage for us to understand black holes. We're going to be particularly interested in those high mass stars, because those are the ones that are going to generate black holes. If you want to learn about low mass stars, we'll cover that another time. Okay? So let's look a little bit more closely then at what happens in a high mass star. You see a dramatic example here on the upper left. This is the famous Crab Nebula, where a star did explode as a supernova. So as I mentioned, the stars will burn or fuse hydrogen into helium. Higher mass stars will then fuse helium into oxygen and carbon and other elements to try to keep their energy going, but it's a losing battle. Eventually, they're going to run out of fuel. Well, when that happens in the center of the star, there's not enough energy to push back against gravity. Gravity now is going to contract this star violently, really collapse this star. And as that occurs, the very center of the star, again, is very small, very hot, very dense. Tremendous pressure now is going to be exerted on that central core. It's going to become extremely dense, so dense to the point that the other matter falling inwardly is literally going to hit that core and bounce backwards. That's how dense that material is. Very much is like if you were to take a golf ball and maybe throw it at a brick wall, it would bounce back at you, wouldn't it? So imagine now the core of a star. It is fused into heavier elements such as iron. And as gravity is contracting this down, it is so powerful that it's literally going to crush the atoms. They're not going to be the familiar atoms that you and I are made out of with electrons and protons. No, those electrons and protons are going to be crushed together by the gravity to the point that they form neutrons. And these are extremely dense little particles. Again, this central core now is where the rest of the infalling material is going to bounce off with enormous energy. We call this a supernova. It's a catastrophic end to the star, as you can see in our diagram here. So neutron stars are the end result of a high-mass star after it has basically lived through its normal life, and that's what we're interested in tonight. Neutron stars set the stage, as I said. They're really the first step in black holes. Now, as I've emphasized the density of these, you see a figure there on our slide, 100 million tons per cubic centimeter. You don't believe me, do you? That's about the size of an old-fashioned sugar cube or maybe a teaspoonful of material, but this is the density that results from this extreme event in space. So these are very bizarre objects, and that makes them, of course, somewhat difficult for us to study. So let's do one more comparison then. Again, I started out by saying, well, our low-mass star is going to end up as a white dwarf star. These are approximately the size of Earth, as you can kind of see here in our diagram. These are relatively dense stars, but you see they're a very tiny neutron star resulting from a high-mass star. More mass than our sun, but squeezed down to a diameter approximately that of Glen Ellen. Hard to imagine that, isn't that? Something so dense. 100 million tons per cubic centimeter. You can imagine that results in extremely strong gravity. You might be somewhat familiar with the law of gravity. It depends not only on the amount of mass that an object has, but on the size of the object, or its diameter, we could think. So the point is, here you have an enormous amount of mass squeezed into a very tiny space. A neutron star has tremendous gravity. So, as you can kind of imagine, they are very difficult to study. However, nature has given us a bonus here. As you can see in my next diagram, neutron stars often give off pulses of light. So how do they do that? Well, first of all, as I said, they're not only very small and very dense, but they are spinning very rapidly. Now, why would they do that? Well, any object in the universe generally has some motion to it. It's hard to imagine something completely motionless. Our sun, for example, is rotating with a certain period. It takes it approximately 25 to 30 days to rotate. As an object like a star rotates, it has a characteristic we call angular momentum. And as the star now shrinks, the object spins faster. Think of an ice skater. Maybe you've seen them go skating down the ice. They put their arms out and they go into a spin. What happens when they pull their arms in? They spin faster, don't they? So because their size has shrunk, the rate of their rotation increases. Well, something far more drastic happens here with our neutron star. This was once a supergiant star, far larger than our sun, and now it's been shrunk down to the size of a small city. So we're going to see some very extreme examples of what's going on here. Not only does the size and spin rate change dramatically, but any star normally has some magnetic field as well. And that magnetic field is likewise going to be very greatly strengthened or concentrated in our neutron star. So we have a small, dense, rapidly rotating star with a strong magnetic field. You can see in my diagram here that this object, if it's rotating in one particular axis, often will shoot radiation out of its magnetic poles. This is very powerful radiation, but it's not directed along the rotational axis, it's directed at a different direction. Well, you might say that's all very interesting. What does this have to do with black holes? Let's get to that point. Let me show you, first of all, exactly what I mean by the pulses of a neutron star. I'm going to show you a short clip here. So here we see our neutron star, and it's rapidly rotating, and it's shooting these beams out along its magnetic axis. We don't normally see that unless we happen to lie in just the right direction that the beam points at us. What do we see? A very intense burst of light, don't we? The point being, we might not normally see that in most neutron stars, again, unless we're in the exact right position for the beam to aim at us. Then we will see a very bright pulse of energy. So think of this. Every time a pulse comes by, of course, we can see that. The time between the pulses would tell us how long it takes the star to rotate, wouldn't it? And so we can figure out how fast the neutron star is spinning. So this is another way for us to study neutron stars, and we can learn a lot about their properties. It's still a very advanced topic, but we are learning quite a bit as we go. So how fast can a neutron star spin? Well, it can spin so fast that, again, we see these pulses regularly coming and going. But we want to press on and talk about the fact that there is a limit to how massive a neutron star can be. As scientists research these objects, they find that the laws of physics demand that they can only be so massive. And that magic number for us tonight, you see there, is 3 times the mass of our sun. So imagine an object, again, neutron star here, that's 3 times the mass of our sun. It can't really be more massive. Why not? Well, let me describe it to you this way. At this point in time, the neutron star has such powerful gravity that for something to escape the neutron star, it would have to travel at an incredible velocity. It would have to approach the speed of light. And many of you are probably aware that the speed of light is the fastest possible speed in the universe. Nothing can travel at the speed of light except light. And so the point being that the gravity is getting stronger and stronger and stronger the more massive this object becomes. What would happen if it reached a certain mass where the escape velocity was the speed of light? In other words, for something, anything, to travel away or leave the star, it must travel that fast. Could anything leave? No. Even light would not be able to escape, would it? So this brings us then to our definition of a black hole. A black hole is an object at which the escape velocity equals the speed of light, and therefore nothing can escape. So it's a very simple definition, but it works for our purposes, doesn't it? You see our artist's illustration here of a black hole. We're going to talk a little bit more about why it appears so distorted, what does it look like. But think of it this way. The escape velocity is equal to or greater than the speed of light. Nothing can escape. This is a black hole. We'll talk about what's going on inside the black hole here in just a minute, but this is a good working definition. So there's really 2 probable ways to make a black hole. Number 1, during a catastrophic supernova explosion of a very massive star, often gravity is strong enough to crush that neutron star past that limit. And as a result, it will proceed to become a black hole. It will continue contracting. It will continue getting smaller and smaller. And no light can no longer escape from it. We also feel it's likely that if we do have a stable neutron star, but for one reason or another, which we'll see later, that it was to acquire more mass somehow, and it went over this limit, it also could collapse to form a black hole. So ultimately, let's think of black holes as coming from neutron stars that go over this 3 solar mass limit. So where's it go? What's it do? What's it like? All these questions, right? Well, the first thing we want to remember is that matter cannot disappear from our universe. It's been proven time and again, there's a fundamental law that states matter cannot disappear from the universe, conservation of matter. And so the mass or the matter is still there, and yet it's at a smaller and smaller and smaller size, and we have no way to see any light escaping from it, do we? So this is indeed going to be a very strange object. That strong gravity is going to, as you saw in that previous image, distort space greatly. In fact, it's also going to distort time. And we'll talk about this as we go along. So you see here some simple diagrams we often use. We sometimes try to picture space as just this flat plane. It's not the best illustration because it's strictly a two-dimensional picture. But notice in our middle image here we have a massive object, perhaps the sun, and it distorts space-time. If you were to get near that object, you would feel space curved and you would follow along and curve your path. Well, a black hole is where space is curved so strongly you would not be able to escape. So we define then what we call the event horizon of a black hole. This is the boundary between being able to escape and not being able to escape. Once inside that event horizon, a certain distance from the center of the black hole, you will not be able to escape because you would not be able to travel at the speed of light. Here's where some very strange effects occur. We need Einstein's theories of relativity to help us understand what may be happening here, but I'll summarize a few things as we go along. I mentioned that even time is distorted. Time will slow down near a strong source of gravity, such as a black hole. So again, some very interesting effects that we'll be talking about as we go along. So again, you see another illustration here of a black hole. It's kind of hard to draw because they're black and space is black. But our artist has kind of given us a nice idea. How big's a black hole? Well, again, it is that distance from the center where that event horizon is. The farther you get from the center, the weaker the force of gravity would become. But there is a certain special distance at which, again, you would need to travel the speed of light to escape. So we call that distance the Schwarzschild radius after the scientists who first discovered that. If you say, well, what's kind of the minimum size of a black hole that might form from a star? Usually, again, we use that number 3 times the mass of the sun. It would only be a few miles across, even smaller than a neutron star. So again, very strange, very interesting type of object here that we're talking about. So what is at the center? Where does it go? What happens inside that we can't see? Well, here's where our theories, our mathematics tell us that, again, gravity ultimately wins this battle. There's no known force to stop gravity from crushing the matter down and down and down, smaller than an atom, smaller than a neutron, smaller than the smallest thing you can imagine. That's our current understanding of what happens at the center of a black hole. We call that a singularity. Again, remember, the mass cannot disappear, but the size is rapidly descending towards zero size. Kind of strange to think of that. And if you then take that one step further and say, well, if the size is approaching zero and there's still a fair amount of mass there, what would the density be like? You know, density, of course, is mass divided by size. So if you divide by 0, what do you get? You get infinite density. That's hard to grasp, isn't it? Hard to grasp what this bizarre object is like. And yet, all the evidence points to their existence, as we're going to see. So you see, again, another diagram here showing a singularity at the center, an event horizon surrounding this object. A lot of interesting things can happen outside the event horizon. Can we know what's going on inside? Well, we cannot observe what's going on inside. We can speculate, we can hypothesize, we can even theorize, we can come up with some ideas that might be true. But as of right now, we can't peer inside of a black hole because no light can get out. So it's an interesting problem for scientists to try to study black holes without being able to look inside of them. Well, can we detect black holes? As a matter of fact, we can. I'm going to take a few minutes now and describe 3 different ways we can do that. As you can see here, they're indirect methods. Black holes do not give off light, so we can't just aim a telescope at one and take a picture. But there are indirect ways to try to detect and study black holes. Number 1, I'm going to talk about the motion of an orbiting star or perhaps some other gas orbiting around a black hole. We might not see the black hole, but we may see its effects on another body. Number two, we often find X-ray type of light coming from a black hole. Now, how is that possible? I thought a black hole doesn't give off light. Well, that's true, but if a black hole were to be taking matter in, we're going to see that that matter, before it falls in, can give off light. And then number three, I want to share with you one of the most exciting, profound discoveries we've just recently made in the last few years, gravitational waves. An entirely new way to study not only black holes, but the universe. So let's take each of these. We'll talk first about the motion of orbiting stars. Now you have to bear with me just 1 minute here. I am going to do just a little bit of math, okay? But it won't be on the test, so don't worry, okay? In the upper right, we can see two stars orbiting around each other. Why do they orbit around each other? Well, you say they have mass and they have gravity, don't they? And they have a certain motion or certain amount of orbital energy, so they're orbiting around each other. And the key there is to think about their gravity. We understand gravity pretty well. We can measure its strength as a force. And so if we look at two objects orbiting around each other and we know the strength of the force, we can determine their masses. How are we going to do that? Well, as you can see here, what we want to measure are the period, how long it takes the two objects to orbit around. And we also need to measure the separation between the two objects. My students have learned all about Newton's version of Kepler's third law. They're probably getting tired of hearing about it. But it's a powerful method for us to be able to find the masses of those two stars by watching their motions. It doesn't always have to be two stars. That's a very common method. It could even just be something as simple as gas orbiting around an object. We could measure the motion of the gas and come to a similar conclusion. So we'll come back to that a little bit later. You can see an equation here. The mass of these two objects together would equal 4 pi squared times a to the third. A designates the distance between them. On the bottom we have g standing for the force of gravity, and then p squared, well, that indicates the period of time. So again, don't worry, I won't ask you to calculate it. But this equation shows us how we can measure the mass of those two objects. So let's put that into practice. In the bottom version, bottom image here, we see what appears to be a giant blue star in the background. And perhaps we are familiar with this type of star. If we're here on Earth, we were to see its light, we'd say, well, it's a big blue star, it's maybe this temperature, and maybe it's this mass. And we understand it relatively well, but perhaps it's orbiting something that maybe is a black hole that doesn't give off light. So that would be very unusual. We might not see it as clearly as you see here, but essentially what would be happening was we would see basically one star appearing to orbit another and not see the other star, would we? So what could we do? Well, again, we would measure the period of time it takes, and we would measure the distance it moves between the two objects. We could get the total mass of both objects in this way. And again, let's presume that we understand that blue star relatively well, and we might say, well, that particular blue star maybe, I'll just say, has 5 times the mass of the sun. But when we measure both together, we get a number, again, I'll pick a simple number, maybe 15 solar masses. So do you see where I'm going here? We know where the 5 masses are, but we don't know where the 10 are that it's orbiting. And if the 10 solar masses don't give off much light at all, it's a pretty safe bet we found a black hole. So you can see how we might indirectly detect that black hole, okay? That would be one way for us to do that, and we've done that. We found a number of black holes using that method. Our second method is to look for bursts of X-rays. Now, why X-rays? Well, you might know that X-rays are a very energetic type of light. It's very high energy light. It's not going to occur just with any particular type of situation, but it's going to require a very high temperature, strong gravity, or maybe both. Picture now, as you see here, a situation where, again, we have a binary system, perhaps a well-known blue star, and perhaps a black hole. Well, that black hole has enormous gravity. And it's very likely that that black hole is going to draw matter off the other star if they're orbiting close enough together. Well, as that matter is drawn towards the black hole, that powerful gravity is going to accelerate it to a very high velocity. It's not going to be able to crash right onto the black hole. No, it's going to shoot past the black hole, But the black hole's gravity is going to pull it back, and it's going to start to spiral around the black hole. And it's going to spiral down almost like water pouring down into a drain because of friction. As this material is spiraling around the black hole, trying to orbit it, it's bumping into other particles, and there's friction involved, there's loss of energy. And so when the material loses energy, it's going to fall in closer. Well, the laws of orbital mechanics dictate that if you move in closer, you must orbit faster. So we basically build up what we call an accretion disk of material that you see here. And that accretion disk is hotter and hotter the closer you get to the center. Well, in some cases, if indeed we have a black hole here, that matter is going to get hot enough to give off X-rays. Our blue star might give off a small amount of X-ray light. But if we're looking at that blue star and we say, boy, that's funny, why is the blue star giving off so much extra X-ray light? It's probably not the star. It's very possibly a black hole pulling matter off, superheating it, that's giving up the extra X-ray light. So again, an excess amount of X-ray light might be a clue to us that we have a black hole here as well. Sometimes enough matter can pile up on that disk that that disk will become unstable and it will explode and give us an extra burst of X-rays. And we've seen this many times. X-ray bursters are well known as sites of probable black holes. So again, you can see that while we don't see a black hole directly, while it doesn't give off light of its own, we have ways of detecting them, don't we? Let me share with you now one of the most interesting, most exciting new discoveries, and that is gravitational waves. Here you see a little diagram showing two massive objects, perhaps two neutron stars, let's assume, orbiting around each other, giving off waves of gravitational energy. And the idea is as they get closer together, as they give off energy, they're going to get closer together. They're losing orbital energy. And as they get, again, moving faster, the closer they get to the center of our point here. So what happens is, because they're moving faster, you can see in our graph that it does take less time for them to orbit around. We can track that in some cases and say those two objects are getting closer together. Well, sooner or later, what's going to happen, of course, is they are going to merge. They are going to crash into each other. There's going to be a tremendous burst of gravitational energy released. That would be our chance. That would be our chance to try to detect a pulse of gravitational energy. Now, how do you do that? How do you find a pulse of gravity? We're used to a very stable gravitational field here on Earth, throughout the solar system. As far as we know, it's normally stable. But again, in this specific case, we could get a burst of gravitational energy. What would that do? Well, it would distort space and time. How could we possibly measure a distortion of space and time? Well, you can probably guess that some very brilliant scientists have kind of figured that out. So let me explain how that works. I'm going to describe our latest observatory called the Laser Interferometer Gravitational Wave Observatory, or LIGO. Now, there are two of these sites in the United States, one in Washington State, one in Louisiana. There are now two more throughout the world, and these are designed to detect waves of gravity. Now, these waves of gravity, by the way, are exceedingly weak. It's nothing you and I would never notice. But picture, again, space itself, which we consider as being fairly uniform, undisturbed, getting a ripple in it, so to speak. It'd be a very interesting phenomenon. How can we measure that? Well, the experiments are designed in such a way that they have two enormously long arms in which they're going to shoot a laser beam. Why are they going to do that? Because we can carefully measure the light of that laser beam, and we can tune it in such a way that if the distance of those arms changes, the light will change. It's extremely sensitive detection. Let's watch one light wave travel down one of the arms. It's several miles long, bounce off an ultra-precise mirror, and when it comes back, these two beams are going to merge together, and if those arms are exactly the same length, our light should be in phase. In other words, we'll get a certain pattern of light over on the right. But if the arms change their length slightly due to a wave of gravity, Notice what happens to the wavelengths of light. They move in and out of phase, don't they? And this is what's detectable. Again, normally, with nothing occurring, the light waves are in phase, but if those arms change length ever so slightly from a wave of gravity passing through them, the waves move in and out of phase, and we can detect that. Now, this is an extraordinarily sensitive device, extraordinarily tiny motion that we're detecting here. The arms have changed in length by less than the diameter of an atom, but we can detect it. And it has been detected now several times, not only in these two locations, but at two others throughout the Earth. Right now, they're making a few upgrades. They're going to improve the facility. And why the two arms? Well, of course, you could have a gravitational wave come from any particular direction. One arm might lengthen, one arm might shrink. That would confirm for you that you indeed found a wave of gravity. So this is really in its infancy, but I think you get a glimpse of the potential here, as we now have an entirely new way to observe the universe. Again, what would be our best opportunity to see something like this? Well, if we had two extremely massive objects like black holes orbiting each other, and eventually they merge together in this enormous burst of energy, something like this. Picture now, again, as they are orbiting and giving off very weak waves of gravity. Sooner or later, they're going to merge, and this would be the opportunity to pick up a more noticeable burst of energy there. This is what we have found. So it's a very exciting time in really the history of all science to have an entirely new way to look at the universe. For centuries, we've used light, and we've used it very effectively. Many of you are aware of that. But now we can literally begin to detect waves of gravity. Here's the results. I know the graph may not look that familiar, but you notice how they match beautifully, don't they? One from Washington, one from Louisiana. This was back in 2015. What they observed with the observatory was exactly what the theory of relativity predicted they would see for a gravitational wave. Now, some of you are familiar with a little bit about the theory of relativity that states that mass and energy, or matter and energy, are essentially the same thing. They can be converted one to the other. A very tiny amount of mass can liberate an enormous amount of energy. Think of our nuclear weapons. A few pounds of plutonium can destroy a city, can't it? So I emphasize that because these numbers are absolutely mind-boggling, hard to grasp. During this merger, these black holes were approximately 30 and 36 times the mass of the sun. But when they merged, the resulting black hole was not 66 solar masses, it was 63 solar masses. The amount of mass in the sun, 3 times that amount, was converted into energy. So this number might help you with that, 10 to the 49th watts. If I were to draw the number 10 with 49 zeros, it's by far the most powerful thing we've ever detected. And so you can imagine the amount of energy here. This literally traveled millions of light years before we even detected it. So mind-boggling that this much energy was converted in less than a second. Yeah, 0.2 of a second. So I think you see the technology here and the new way to see this type of event. But for our purposes tonight, it's an amazing way to actually detect two black holes merging into a bigger one. We're going to come back to that theme as we continue along now, because if you think about it, it starts to make sense that black holes could grow in mass, couldn't they? So that's where we're going to go. How big can a black hole get? How massive can it become? Well, we said that they really start out with stars, don't they? And maybe as small as 3 solar masses, maybe a little bit more. So we think of stellar mass black holes as being perhaps, again, 3, 5, 10, 20, something like that. But if that black hole were somehow to be able to draw matter in, it would grow in mass. And we mentioned earlier that Schwarzschild radius would slowly get larger. Won't grow fast, but it will grow, and so our black hole itself will become larger. Here you see yet another example of an illustration showing a black hole perhaps orbiting another star, perhaps pulling matter off of it, growing in mass. So how big can they get? Well, this has been an interesting question astronomers have been pursuing. I'm going to give you a few examples. First, we've looked out into different star clusters. You see a few here. I'll start on the lower left. This is a globular star cluster surrounding the Milky Way called M15. We've detected a black hole with 4,000 times the mass of the Sun. In the center, you see a globular star cluster from the Andromeda galaxy. Many of you are familiar with that, our neighboring galaxies. This is much farther away, 20,000 times the mass of the Sun. And on the right, the Omega Centauri cluster, which orbits the Milky Way, 40,000 times the mass of the Sun. Now clearly, these can't be black holes that form directly from a star, can they? There is no star with that amount of mass. These grew some other way. It seems certainly likely that they formed by the merger of other black holes. One of the clues there, as we're going to see in the next few slides as well, is that these black holes are in the center of these star clusters. And you can tell even just by looking at our diagram here that that really means there's an awful lot of stars in that area, aren't they? They seem very crowded together, don't they? Now, there's still plenty of space between them, but they're certainly closer together than maybe they are in our part of the galaxy. Well, astronomers have looked at other galaxies as well. Now, we can't see individual stars very clearly in other galaxies. They're simply too far away. But we do have another way to detect them. So let me explain how that would work. Here we have a diagram I'm going to show you at the center of the Milky Way. And what astronomers decided to do was to use method number one we talked about, where we're going to measure the motion of a star as it orbits what might be a black hole. Again, we said earlier we need to measure the separation between them. We need to measure the amount of time it takes. We can go back and use that equation, plug that in, determine the mass of both objects. Now, it turns out in this case, the stars themselves, their mass is relatively insignificant. But watch what happened when a group at UCLA some years ago started to watch these stars slowly orbiting around the center of the Milky Way. Notice how they zip around, and they've put a little artificial star here. How cute, isn't it? To be able to show you where they are moving from. Notice this one from the upper left, zipping in around, and the one from above, orbiting around the center. Well, by carefully, again, measuring the amount of time and the separation, we can measure the mass of that central object. And you can see the number. 4 million times the mass of the Sun. So even astronomers had to come up with a new name, a supermassive black hole in this case. So this was quite a dramatic discovery back about 10, 15 years ago, to be able to see the motion of those stars as they move around that center of the galaxy betrays a supermassive black hole. Now, does the whole galaxy revolve around this black hole? No, it certainly does dominate its immediate region, its immediate environment here. Those stars are orbiting around it at millions of miles per hour, but its extent doesn't reach out to where we are by any means. Well, that was very interesting. Just recently, I located the very latest result from a similar effort to try to look into the center of the Milky Way and see it as best we can. Now, they haven't quite got a picture of a black hole yet, sorry. But what they have done is measure very carefully additional objects, and they've taken that information and they have made it into a little video here that shows what it might look like to see some of the gas swirling around the black hole. You can see that glow of light there and some of it being distorted. So this is a very interesting observation to be able to see what that might look like. We think in the next 10 to 15 years we may actually get a picture. Again, the black hole itself won't be giving off any light, will it? But we may well see material swirling around it. Wouldn't that be a dramatic actual image for us to see? So scientists are hard at work to make progress, to learn more, to analyze more, understand more about black holes. Well, again, I mentioned we can't see individual stars in distant galaxies, but we do have another way instead to see if maybe there's a black hole there. I mentioned back that we might also be able to measure as gas is maybe swirling around a black hole. That gas is going to have a certain high velocity. And many of you are familiar with the Doppler effect? Material that is moving towards you, its light has a very slight shift in wavelength. If it moves towards you, it shifts to the blue. If it moves away from you, it shifts to the red. Astronomers could take advantage of that, and they can use that to look into other galaxies. So here's the galaxy M84. We're looking into the very center, and notice this beautiful colored diagram is indicating that on one side of the center, the material is approaching us rapidly because its light has a blue shift to it. On the other side of the very center, the light has a very strong red shift to it because it's moving away. In other words, the light is basically, or the material rather, is moving towards you and away from you. In other words, it's a swirling disk. And by measuring the amount of the shifting of the light here, we can measure the velocity of this material orbiting around the center. And we can go back and use that equation. And we can then determine the mass of the object in the center. You can see an even bigger number, 300 million times the mass of the sun. What a mind-boggling object that must be. Imagine now a black hole, 300 million solar masses, 1,000,000 times, or rather 100 times more massive than the one in our solar system. By now that Schwarzschild radius has grown and grown and grown. This thing could easily fill much of our solar system. That is a pretty impressive supermassive black hole. We have one more here in the galaxy cataloged as M87. Once again, we peer into it. We carefully measure the motion, velocity of that gas. We take that equation and we calculate the number 3 billion solar masses. This would be the size of our solar system. So that's a big black hole. That is an amazingly big black hole, is it not? Again, these are not objects that formed from stars. These are objects that have been merging over long periods of time. It's quite likely that over time other black holes have merged with it. And of course, the larger, more massive, and more powerful its gravity becomes, it's going to draw in even more material, isn't it? And continue to grow and grow and grow. So astronomers are hard at work to understand not only this process, but what does that mean really for the whole understanding of galaxy formation in the ancient past, how they've changed over time, in other words, the evolution of a galaxy. How does that work out? In other words, was the black hole maybe an early seed to the galaxy and the galaxy formed around it? Or conversely, could it be that the galaxy formed and any massive object that turned into a black hole gradually migrated to the center? We think it could be either or both. We're still kind of working on that. We have to look back at galaxies at different ages and different distances to see them at different points of development and try to piece together that life cycle. So again, a fascinating branch to go off into and try to analyze and understand what black holes can tell us even about the history of galaxies. That's an interesting question for us to understand if we want to make sense of the big picture of our universe. Want to visit? I wouldn't recommend it, but there's always a few that just want to go. Well, before you do that, let me explain what you might expect. First of all, I've mentioned several times Einstein's theory of relativity. We saw that the powerful gravity is going to distort the light around the black hole dramatically. Number two, the gravity near a black hole changes dramatically. In other words, as you see on the left here, an astronaut who chose to jump into the black hole, the force of gravity on his feet is going to be much stronger than the force on his hands. So in other words, it's going to stretch him apart. Neil deGrasse Tyson likes to call this spaghettification. He likes to say, you know, when I go, I mean, at least I'll jump in a black hole or something, you know, so okay, whatever. He says you get stretched out and he can get kind of graphics, you know, your atoms are getting ripped apart and all this. Okay. Anyway, the point is tremendous what we call tidal forces. The gravity increases dramatically, so it doesn't sound good for any type of object or potential spaceship to try to dive into a black hole, does it? It's going to get ripped apart. We mentioned time passing more slowly near the event horizon. That'd be some very dramatic effects. How many saw the movie Interstellar? Did you see that movie? If you haven't, you should see it. It's good. It's all about black holes. But the point is, there's one scene in particular I really liked, because in one scene, the astronauts are going to go near this black hole, and one astronaut stays up in the main ship, and two of them go down much closer to the black hole. And they dramatize exactly what I'm talking about here. For the two that are down near the black hole, time flows much slower for them. This astronaut waiting up here is waiting and waiting and waiting. Finally, they come back after several hours, and they open the hatch and they say, how long were we gone? And he has this look on his face like, about 23 years. And that's very possible. That's very possible. It's not something wrong with their clocks. It's not anything of a trick. Time would actually pass differently for those people, depending where you were. Some of my other lectures have talked a little bit about that in the theory of relativity. We can actually prove that on a smaller scale, not that dramatically, but we've actually measured very slight differences in how time flows under various circumstances here on Earth. So, got to tell you, if you travel to a black hole, when you come back, we're all going to be a lot older. Okay? So think it over carefully before you decide to jump into a black hole. But let's take one more look here at what it might look like for us. We're going to step back and watch as we dive in. In the distance, you see our black hole approaching, and again, the great distortion of space. And don't forget about time. On the left, you see a green circle showing from above as we're coming in closer and closer. We're spiraling in to the black hole. When we reach the red, that will be the event horizon. Now, you wouldn't see these funny-looking lines, but they are trying to show you how space is distorted from a flat grid. That started out as a flat grid. And notice the tremendous distortion as we now dive in just inside that event horizon. You can see the light kind of pooled above us. We're not getting out. And that's kind of what it would look like. So kind of a dramatic, extreme view here of what you would see if you dive into a black hole. You're not coming back. So I think you get a real sense of, again, the extreme nature of these objects, how bizarre they are, how they challenge our normal experience, our everyday life. This would be a very extreme situation. You probably wouldn't live real long to experience it, but that is what it would pretty much look like. Okay? Well, let me finish up with one other very interesting possibility for you science fiction fans out there. Maybe you've heard of this term wormholes. Have you heard that? So some have said, well, you know, if there's a black hole here and the matter is going in there, where does it go? Can't really say, but is it possible that space-time is curved and distorted so much that that could be connected to another black hole over here and almost kind of give you like a shortcut through space-time? You see a little artist's illustration of that here. A wormhole, kind of a tunnel through space, through the dimensions of space. Well, it seems pretty far-fetched, but I got to tell you, the theory of relativity allows for it. It's not going against any known physical laws. And time and again, we've been surprised. It seems that if something is possible, nature often does allow it, and nature often does build it. There's other examples we could give of that, so we just don't know. I will tell you the bad news, though, is there's no known way to survive, because again, if you fall in a black hole, your matter is going to get crushed down beyond the small size of an atom. Atoms will not exist anymore. There's no more familiar electrons and protons and neutrons that you and I are made out of, so don't get your hopes up. But it is, as I like to say, it makes for good science fiction for us to think, well, is it possible to do this or do that? And time again, we've discovered things we never imagined. You think back to the 19th century, they had no concept of something like this, and here we are 100 years later talking about them as real objects we can study. So there's kind of a saying, never say never. We just don't know what we don't know. And who knows, if you cut back in 50 years, 100 years, I'll have to update the lecture, but we might know more. Who knows what we will discover in this vast, amazing universe. So in conclusion, I think you've seen, again, some pretty dramatic characteristics, qualities of black holes. What are they like? Where do they come from? How big are they? What's it like inside? We have a lot of answers, but they just tend to raise more questions, don't they? We don't know a lot of what we'd like to know. Questions are scientists' first step, aren't they? We'll make some observations, right away a question comes up. Well, what about this? What about that? And nowhere is that more apparent, I think, with black holes. So what will they teach us next? We don't know, but I sure would stay tuned. Thank you very much for coming tonight. Nice to have you. The theorized temperature of a singularity. That's a tough question. We have to go back to our definition of temperature. What is it? What do we mean by that? And we may have different ideas or understandings, but ultimately temperature refers to the amount of energy in the particles of a body. You heat a body up, the particles have more energy. You heat up a solid enough, of course it melts. You heat it up even more, it's going to turn into a gas, so on and so forth. So the problem becomes that, as I said, we're not able certainly to observe inside the black hole and take any measurements. We would have to theorize, wouldn't we? We'd have to say, well, what could happen down there? And as you saw, the mathematics lead us quickly to things like infinite density, zero size, those kind of things. So the problem becomes that, again, we don't have a way to theorize exactly what that temperature might be. We know that matter falling into a black hole is going to be superheated by the gravity and the tidal forces, but there's no way to know exactly what the temperature would be at the center. So would it be absolute zero? It's unlikely because, again, that matter is extremely compressed, extremely hot going in. Is there some maximum ultimate temperature? No, not really. There is certainly the point where atoms are moving so fast they're going to approach the speed of light, so you would reach kind of a practical limit, but it's just hard to say what that might be. So that's an interesting question. If something could escape a black hole, why could light not escape it? Unfortunately, that's really part of our definition. In other words, light cannot escape it. And since nothing can go as fast as light, nothing else is going to be able to escape it. So that's why it's really kind of the ultimate boundary there. You don't want to get inside that boundary because there's no known way to come back out. So the question is, if black holes are merging over time, will that eventually begin to suck in the whole universe? And the short answer is no. That might seem possible in theory, of course, over enormous amounts of time. But one of the things that we want to remember, fortunately, is black holes are relatively small and the universe is enormously big. So I highlighted that the center of the Milky Way, we do have a large, massive black hole, but it doesn't dominate our entire galaxy. The distances are too great. So we're safe for quite some time. It's a good question, though. So this is an interesting question as well. Neutrinos were brought up. Neutrinos are particles that interact very, very weakly with matter. They normally fly right through. In fact, I hate to tell you, this entire time they've been flying through you. They fly through the sun. They don't interact, hardly at all. They're extremely difficult. How would a neutrino fare in a black hole? We think something similar is going to happen. It is affected, but we don't know the details of it yet. We're still kind of studying that. In other words, the gravitational effect, what does that have on the neutrino? The radiation effect, all those kind of things will come into play. We don't have exact answers yet on how neutrinos and black holes interact in detail. If I heard you correctly, I think that's Andrew, the size of the object that causes the event horizon?
Yeah, so whatever, like, because it's supposed to be really small, correct?
Yeah, so again, as we discuss, we have an object of such mass, and again, often they're formed during supernova, the extreme event there I know you're familiar with. And the point being that you have such strong gravity, we now get past the point where anything can escape. Gravity continues to crush to smaller, smaller, smaller. The event horizon is not a physical surface that you could walk up to or fly up to and land on, anything like that. It is a boundary, I like to use the term, or a distance from the center, at which at this distance, I better have a rocket that can make me go this fast to escape, otherwise I'm falling in. So again, it's not so much a physical boundary as it's a boundary of here's where light no longer can escape. Okay, so if I heard your question correctly, the size of the object comes back to really the mass. Is the mass great enough to form that strong of a gravity in such a small space to cause that event horizon? So the question has to do with LIGO has been observing black holes of approximately 30 to 40 to 60 solar masses colliding. These are binary black holes. Obviously started out as very, very massive stars. Both went through that cycle I described in the beginning. Both turned into black holes. They're still orbiting each other, but because they're black holes, they tend to lose that energy faster than maybe a normal star, spiral together and merge. Why aren't we seeing mergers of black holes with greater mass? We're just now kind of getting those first few measurements, and we don't know how many black holes exactly there may be and what their masses may be. In fact, these first few events gave us our first real look and to say, oh, there are black holes at 30, 36 mass. We strongly suspected it. Stellar theory tells us they should be there, but this was actually, again, a very new way to actually confirm that and say, yeah, there really are black holes of that mass. I suspect in time we're going to find. In other words, I think what you're saying is, well, did we see a black hole of 80 solar masses merge with one of 80 or something like that? Okay, so the very largest mergers in these centers of galaxies that are millions of solar masses. Why aren't we seeing that? Because those are going to be multiple smaller mergers. Maybe that's the answer. In other words, you don't just have 2 million mass solar black holes merge all the time. It can happen. In fact, what we think one of the best places to watch for that will be as galaxies merge. If each galaxy has a central black hole and they merge, that's going to be quite an event. You might know that we think that millions of years in the future, the Andromeda Galaxy and the Milky Way galaxy are going to merge. That would be a titanic merger, wouldn't it? The energy involved. A million solar masses here, several million here. So I think that's kind of what you're staying up to watch. So anyway, I think we will see some of those as we go along. How fast do gravity waves travel? They travel at the speed of light. They travel at the speed of light. So again, the ones we've seen have been quite distant in other galaxies. We haven't seen one nearby. So that gives us a clue that they're not happening every day in our galaxy. Why not? Because black holes come from massive stars, and I don't think I mentioned this, but massive stars are relatively rare. There's not nearly as many of the high mass stars as there are the low mass stars. Okay, so if the high mass stars are relatively rare, the black holes are relatively rare. We won't see a lot of mergers, but the ones we've seen have been in other distant galaxies. Okay. So I believe the question was, if we have massive objects and we made clear that time flows at a different rate near those objects, if you get closer to them, if they were to collide, what would be the extent now of the time distortion?
Sorry, I worded it badly, but essentially if you have such a large mass and it disrupts it, like it goes so far down that time is changed to such a great extent. You know, do we have like a calculation of how large this extent of change is?
So we can calculate, the theory of relativity enables us to calculate how much time distortion there would be depending on the strength of the gravity and your distance from it. We've measured, again, in a very minuscule amount, we've placed atomic clocks in the basement of a building and put them up 30, 40 stories on a building and watched, and over time, they slowly drift apart, just with Earth's weak gravity. So if it's a more massive object, it will distort time more, time will go slower. If you're closer to it, if two objects merge, certainly their combined mass is going to, again, increase the amount of distortion. So black holes, what's the ultimate fate?
Yeah.
Black hole seems to be pretty permanent, unless you ask Stephen Hawking. Okay, we can take this on. So Stephen Hawking, recently deceased, found what he thought was an effect we now call Hawking radiation. And you say, well, what's that about? I thought nothing can come out of a black hole. Well, not usually, but some are a little bit familiar with the field of quantum mechanics, and this deals with the very, very, very small atoms, subparticles, things of that nature. Turns out if you go down and down and down to the smallest sizes, smaller than an atom, smaller than a proton, smaller than an electron, smaller, way, way down in size, what is space-time like? Well, we try to use different terms to describe it. It's rather difficult, but sometimes we'll talk about the fabric of space-time. Like, what is it? Is it anything tangible? And it turns out that experiments have clearly showed that there is some non-zero amount of energy in space. And there's also principles, one called the uncertainty principle, that says, well, we can only look down so far, and beneath that there is an inherent, unavoidable uncertainty in what level of detail we can know about the extremely small. And below that level, things could happen that we're not necessarily aware of or might not make a lot of sense. Now, I mentioned earlier that mass cannot disappear from the universe, and it can't just appear magically out of nothing, but beneath this level of uncertainty, there's no way to enforce the rules. In other words, Hawking says, well, what if we had two particles, one a normal particle and one is antiparticle, and they just sort of magically appeared out of the energy of space, as long as they disappeared quickly enough that we couldn't measure them, could that happen? And you say, well, I suppose. I mean, where are you going with that? Hawking says, well, that could be happening anywhere in space, couldn't it? And as a matter of fact, we have measured very real effects to confirm that. Go home and look up the Casimir effect. Back to the question. Hawking says, could that effect take place right near the event horizon of a black hole? I suppose it could happen anywhere, right? So picture now two particles pop into existence for an incredibly brief amount of time. Unfortunately, one falls into the black hole, and it cannot annihilate its partner and go away. Well, this partner's left with no one to annihilate it. It might escape. It might escape. If it was an antiparticle, you could almost envision this as being more of a negative effect, that not so much that the black hole gained mass, but that the black hole lost a negative particle. So the point of Hawking's idea here is you get this Hawking radiation of virtual particles, these are called, and some of them are escaping from the black hole. The black hole's mass is actually shrinking. So it's a very extreme, unusual effect that Hawking worked through, and there was a lot of controversy. Not everyone agreed with him, but the idea has stuck around. So do black holes last forever? We would say yes, except for Hawking radiation. Now, even that, how long will that take? Many times the age of the universe for a normal-sized black hole. Oh boy. So in other words, if we have the merger of two black holes, and there's this burst of gravitational wave, what happens to any matter nearby that? It gets distorted. You don't want to be there. You would get stretched in one direction and squished in the other. Space itself would literally distort. It would be a very bizarre thing to see or experience. But yeah, matter would be greatly distorted, I guess is the right word for it. So you don't want to be anywhere near that. They are. My lectures are on YouTube now. I've done several in the past. This one tonight. There are also some other examples you can see here to go out and view at your convenience. If a black hole came near the Earth, how close could it get without wiping out humanity? That's an interesting question. Before it were to directly affect us, it would almost certainly affect the other planets, especially our sun. If black holes somehow manage to come near our solar system, the sun, of course, being more massive, and our source of heat and light and all that is going to be affected. That would probably have a quick indirect effect on us. Our orbit could be affected, sure. Planets' orbits could be distorted and redirected and so forth, and that would be a bad thing for us, yeah. So, as I said, the good news is space is really big and black holes are really small, and they're not all that common. And by that I mean there could easily be tens, hundreds of thousands, maybe even millions, but space is awfully big. So I think we're safe for now. Thank goodness, okay? Yeah, how many? Again, if we look at the statistics of stars, we see a dramatic decrease in the number of stars as the mass increases. So earlier I said high mass stars are very rare. Those are the ones that make black holes. In the Milky Way, we have about 200 billion stars, roughly speaking. And of those, it's less than 0.1% that are the most massive stars. So you can get a rough idea how many there should be. And then you could say, well, the volume of the Milky Way is this much. How far apart should they be? On average, they should be many thousands of light years apart. The nearest one that's been detected is some thousands of light years away, yeah, towards the constellation Cygnus. Go home and look up Cygnus X1. And you'd say, oh, that's interesting. One of the first ones we discovered. Yeah, so again, everybody's a little concerned about this, but we're good for now. So I believe the question was, if the universe, since the universe is constantly expanding, are the black holes moving farther and farther apart? Kind of a yes and no answer to that. In other words, when we hear of the universe expanding, remember that it's really galaxies that are moving apart. The Milky Way galaxy has enough gravity to hold itself together. It is not expanding, but it is moving apart from most other galaxies. Now, black holes within the Milky Way are going to pretty much stay within the Milky Way. But on the other hand, if you were to say, well, what about the black hole in the Milky Way and the black hole in that galaxy? Yeah, I suppose they're moving apart. But it's really the whole galaxies that are moving apart. So the expansion of the universe is not having a huge effect on black holes. Yeah, that's a good question. Do black holes spin? Stars spin. White dwarfs spin. Neutron stars spin. Black holes spin, right. When black holes were first discovered theoretically, they were found to be exceedingly complex to describe mathematically. And some theorists sat back and said, well, wait a minute, let's just talk about a black hole that doesn't spin. It'd be a little easier. And they kind of learned a lot about black holes. And then they realized, of course, we do need to go back and add the spin back. And that does complicate things. It does complicate things, I can assure you. The black hole right near that event horizon as it's spinning is literally dragging space-time with it. Any massive object will do that. Our sun has a very slight effect to that. But the point is a black hole, yeah, is normally spinning, yes. So as a black hole grows, how fast will it spin? That depends on a lot of factors, yeah. I think that's a question that requires fairly advanced mathematics. Relativistic effects will come into play there. So that's a good question. I don't know the exact answer. But I hope you'll come back and join us again on February 9th. We're going to talk about the Hubble Space Telescope. Again, thank you for coming. Have a wonderful night.